Have you ever looked at a graph and just seen a bunch of lines and numbers? Well, today, we're going to change that. We're going to see how these simple charts aren't just data. They're actually stories. Complete stories of a journey, just waiting for someone to come along and read them.
And that's really the big question, isn't it? How can one single line on a page tell you everything? Not just where something went, but how fast it was going, whether it was speeding up or slowing down, and even exactly how far it traveled. It's like a whole visual language, and today we're going to learn how to speak it fluently.
So, where do we start? Well, like with any new language, we've got to learn the alphabet first. Before we can piece together the whole story of a journey, we need to understand the basic words and phrases of these graphs.
Now, there are two main types of motion graphs you'll run into. There's the distance time graph, where the slope of the line tells you the speed. But today, we're focusing on its cousin, the velocity time graph. And here's the absolute key difference. On this graph, the slope of the line represents acceleration.
So, what even is acceleration? It's really just a fancy word for any change in speed. Is the object hitting the gas? Is it slamming on the brakes? That change, that speeding up or slowing down, is what we call acceleration. And on our graph, it's all shown by how steep that line is, the slope.
All right, so if the slope is acceleration, what do all the different kinds of slopes actually tell us? Let's break down the different shapes a line can make. Think of these as the three basic words that are going to build our entire story.
And honestly, it's super intuitive. Think about it. If the line is going up, that means the velocity is increasing. The object is speeding up. Simple. If the line is totally flat or horizontal, well, the velocity isn't changing at all. It's just cruising along at a constant speed. And if the line is sloping down, you got it. The velocity is decreasing. The object is slowing down. Up, flat, down. That's really our core vocabulary.
Okay, we've got the alphabet. Now it's time to read our first story. We're going to follow a car on a quick trip and build its velocity time graph from scratch. Let's put all this theory into action.
So let's picture our hero for this story, a Toyota car. Right now, it's just sitting there, not moving. It's at rest. So its velocity is 0, which means we're starting right at the very bottom left corner of our graph. Okay, the driver puts their foot on the gas. For the first 2 seconds, the car smoothly speeds up from 0 to 4 meters per second. And on our graph, what does that look like? A perfect straight line sloping upwards. That right there is a picture of positive acceleration.
Now, the driver reaches their desired speed and eases off the pedal a bit. For the next 4 seconds, the car just cruises along at a steady 4 meters per second. No speeding up, no slowing down. And our graph? It becomes a perfectly flat, horizontal line, showing us there's 0 acceleration.
Uh-oh, red light ahead. The driver hits the brakes. Over the last 2 seconds of our journey, the car slows right down from 4 meters per second back to a complete stop. And just as we'd expect, our graph shows a nice, steady downward slope, all the way back down to 0. And look at that, we've drawn the complete story of a journey in one simple shape.
And we can even prove this with some really simple math. Remember, slope is just the change in velocity divided by the time it took. So for that first part, the acceleration, it's a change of 4 meters per second over 2 seconds. 4 divided by 2 gives us 2 meters per second squared. For the end part, the deceleration, the change is -4 over 2 seconds, which gives us -2. The math perfectly matches the picture.
But hang on, we're not done yet. The slope told us all about the car's acceleration. But this graph is holding on to another secret, an even bigger one, actually. It can tell us exactly how far the car went.
So yeah, we've nailed down the how of the car's journey. It sped up, it cruised, it stopped. But what about the big question? How far did it actually go? Can our little graph really tell us the total distance it covered?
You bet it can. The answer just isn't in the slope this time. No, for distance, we have to look at the space underneath the line we drew. Here's the magic trick. The total distance traveled is equal to the total area under that line. This is a huge idea in physics.
Now, I know what you might be thinking. That whole shape looks a bit weird, kind of like a trapezoid. How do you calculate the area of that? Well, you don't have to. We can just break it down into the 3 simple parts of our journey. We've got a triangle on the left, a rectangle in the middle, and another triangle on the right. Easy.
All right, let's crunch the numbers. For that first triangle, the area is half the base times the height. So that's half of 2 times 4, which is 4 meters.
The rectangle in the middle is even easier, length times width. That's 4 times 4, which gives us 16 meters. And the last triangle is just like the first one, so that's another 4 meters.
So what's the grand total? We just add them up. 4 meters from the start, plus 16 meters from the cruise, plus another 4 meters while stopping, gives us a final answer of 24 meters. Incredible, right? Just by looking at the shapes, we figured out the exact distance the car traveled.
So let's take a breath and recap. In just the last few minutes, you've basically built a complete toolkit for reading the story of any journey from one of these velocity time graphs.
Let's put it all together. The vertical y-axis, that's your speed at any given moment. The horizontal x-axis, that's time. The slope of the line, that tells you about acceleration, speeding up or slowing down. And the area underneath it all, that's your total distance. 4 simple rules that unlock the entire story.
What this all really means is that a simple graph is way more powerful than it looks. A single line, drawn on a grid, lets us see and calculate every important piece of an object's motion. It's a whole story, told in the beautiful language of physics.
So now you know how to read the story of a journey. And that really makes you wonder, doesn't it? If one little line can tell us all of this about motion, what other amazing, complex stories are out there, hiding in other graphs, just waiting for us to learn their language?